In order to use a BST to search for items, we need to first store all the items in the BST. A BST starts off as a single root node. Then we insert new nodes one by one until all the items are in the BST. In this lesson, we will use the AVL tree insertion algorithm to insert the nodes. Our main objective is to ensure that the tree remains a balanced BST after the insertion is complete. Our strategy is to search the BST for a value that we're trying to add. Then, when we reach a leaf, we add the new child node either to the left or the right, depending on whether the new value is less than or greater than the leaf. Finally, if the tree becomes unbalanced, we will balance the tree. For example, let's try adding 2 to this example tree. Let's begin by searching the tree for 2. We start at the root node 5. 2 is less than 5, so we follow the left edge. The next node is 3. 2 is also less than 3, so again we follow the left edge. The next node is 1. 1 is a leaf, so the search is over. 2 is greater than 1, so 2 should be the right child of 1. Here's the tree after we insert the new node 2. Next, let's check if the tree is still balanced. The height of the left subtree of 5 is 3. The height of the right subtree is 1. The difference is 3 minus 1, which is 2. And 2 is greater than 1, so the tree is not balanced. How do we balance this tree? The general idea is to tilt or rotate the tree to increase the height of the shorter side and decrease the height of the taller side. If the left subtree is taller than the right, we rotate clockwise, and the left child becomes the new root. Conversely, if the right subtree is taller than the left, then we rotate counterclockwise, and the right child becomes the new root. In the example above, the left subtree is taller, so let's try rotating clockwise. Here is the result. Node 3 cannot have 3 children, so we removed node 4 and attached it to node 5. Node 4 is now a left child of node 5. In general, if we are rotating clockwise and the left child has a right subtree, then after the rotation, the right subtree will become the former root node's left subtree. Notice that since the left child became root, the former root conveniently no longer has a left child. Thus, we're able to place a new left child. Here's a video demonstration of case 1. Now let's discuss the performance of this algorithm. First, cost of inserting a new leaf node is equal to the cost of searching the tree plus the cost of creating a new node and linking it to the parent. We know that the search cost is O log of n. We don't know the exact cost of creating a new node and linking it to the parent, but the cost is fixed. Fixed means that the cost is the same whether the tree has 5 nodes or 5,000 nodes. Since the cost does not depend on the number of nodes, in big O notation, the cost is O of 1. Thus, the cost of inserting a new leaf node is equal to O of log n plus O of 1, which is just O log of n. As n becomes large, O of 1 becomes insignificant, so we can ignore it. Then we need to know whether the tree is still balanced. This requires us to compare heights of subtrees. If we have to calculate the height of every subtree, we would need O of n operations, which is undesirable. But if we store the calculated height in the node, then we do not have to recalculate it unless a subtree of that node changed. Then we only have to calculate the heights of the new node and its ancestors, which costs O log of n operations. Finally, we may need to balance the tree. The rotation consists of the following. Step 1, disconnect node 5's left child. Step 2, disconnect node 3's right child. Step 3, node 5 becomes node 3's right child. And step 4, Node 4 becomes node 5's left child. The rotation costs 4 operations and perhaps a few more to retrieve the 3 changing nodes. More importantly, rotation costs a fixed number of operations, or O of 1. Now let's add all the costs to get the total cost. The total cost is cost of insertion, cost of balance check, and the cost of rotation. And those costs are O log of n plus O log of n plus O of 1. And the total cost is O log of n. Now consider a slightly different example. Suppose we add 8 to this tree. Then the result is this tree. The left subtree has height 3, and the right subtree has height 1, so the tree is not balanced. Since the left side is taller, we can try to rotate clockwise. But notice that the tree is still unbalanced. This time, the height of the right subtree is 3. Let's compare case 1 with this new case. In both cases, the new node was added to the left subtree, but in case 1, the node was added to the left child's left child, whereas in this case, the node was added to the left child's right child, or left-right. In the first case, we can simply rotate clockwise, but in the second case, we must perform 2 rotations. 1. A counterclockwise rotation of the left-right grandchild to the left child, and 2. A clockwise rotation of the left child to the root. Here again is the tree after 8 was added. Let's rotate the left-right grandchild, or 7, into the left child, or 5. The tree is now in the same state as case 1. Thus, we rotate the left child, which is 7, into the root, as before. Note that we had to move the left-right child to the left node of 10, as before. Now both subtrees have height 2, so the tree is balanced. Here's a video demonstration of case 2. Like in case 1, we first added a new leaf. The cost is the same at O of log n. And again, we checked if the tree was balanced. This cost is also the same, or O log of n. But unlike in case 1, we had to rotate 2 times. Both rotations cost O of 1 operations. Now let's add all the costs to get the total cost, which is the cost of insertion plus cost of the balance check plus 2 times the cost of rotation, or O log of n plus O log of n plus 2 times O of 1, and the total cost is O log of n. Let's consider one more case. Consider the following tree again. Suppose we add 6 instead of 8. Then the result is this tree. Let's balance this tree. Once again, the element was added to the left-right grandchild. So first we try to rotate node 7 into node 5 as before. Node 5 became node 7's left child, but node 7 already had a left child 6. Node 7 can't have 2 left children, so we have to move either node 5 or node 6 elsewhere. Conveniently, node 5 no longer has a right child, since node 7 became its parent. So node 6 becomes the right child of node 5. In general, if we're trying to rotate the left-right grandchild into the left child, and the left-right grandchild has a left subtree, then the subtree becomes the right child of the new left-left grandchild. This is actually a mirrored version of case 1's rotation, where node 4 was detached from the old parent and became a left child of the new parent. Now we can move node 7 into the root as before. Here's a video demonstration of case 2. Now let's look at case 2.2's performance. Like in case 2, we first added a new leaf. The cost is the same at O log of n. And again, we checked if the tree was balanced. This cost is also the same at O log of n. And like in case 2, we had to rotate 2 times. And although the first rotation has a couple of extra operations, the rotation cost is still a fixed number. Thus both rotations still cost O of 1 operations. Thus the total cost is O log of n, as in case 2. So far, we have inserted all values to the left subtree. The process of inserting a value to the right subtree and balancing the tree is a mirrored version of inserting to the left subtree. For example, consider this tree. Suppose we want to add 7 to this tree. Then the result is this one. This is a mirrored version of case 1. In case 1, we rotated the tree clockwise. So let's rotate counterclockwise. In case 1, the left-right grandchild became the new right-left grandchild. And here, the right-left grandchild became the left-right grandchild. We can also mirror cases 2 and 2.2 to cover the rest of the right subtree insertion cases. Since the insert operations on the right subtree are just mirrored versions of cases 1 to 2.2, the costs are the same at O log of n. As we can see, the cost of insertion is O log of n for all cases. This means AVL tree insertion is asymptotically faster than linear stack insertion.